So today we're diving into a really powerful idea. What if good teaching isn't some random art form, but a science that we can actually design? We're going to break down how you can plan instruction that genuinely works for every student, just by understanding the basic logic of how we all learn. All right, let's get into it.
You know, this is the question that probably keeps a lot of educators, and parents for that matter, up at night. You teach a concept, some students just get it, boom, right away, and others are just completely lost. It's so frustrating, and it can feel like some kids are just, well, destined to struggle. But what if the problem isn't the student at all? What if it's the instruction?
And this is where we get to the absolute core of the problem. This quote right here is a bombshell. It's suggesting that when we use flawed instruction, it creates this illusion that we're succeeding. Why? Because the strongest learners, they can fill in the gaps themselves. They overcome our mistakes. So the teaching looks like it's working, but it's completely failing the students who rely on us for clarity the most.
So what does that actually look like in a classroom? Well, a strong learner can see a messy, confusing example and just filter out all the noise. But a struggling learner, they need explicit focus. A strong learner can make a logical leap that you forgot to include, but a struggling learner needs every single step to be systematic. And here's the crucial part. The burden of a design flaw always falls on the student who's already having a hard time.
Okay, so if flawed design is the problem, what's the solution? Well, the answer is in understanding the hidden logic of learning itself. See, learning isn't some kind of mysterious magic that just happens. It's a predictable, logical process that's going on inside every single student's mind.
And that process, it has a name: inductive reasoning. It's basically the same method a scientist uses in a lab. You look at a bunch of specific examples, you see what's the same, you see what's different, and from all that evidence, you form a general rule. This is how we learn everything, from what a dog is when we're a toddler to the laws of physics.
We can really break this down into 3 simple steps. First, we give a student some examples. Second, their brain just automatically gets to work finding the patterns, what's consistent and what's changing across these examples. And third, based on that, they form a general rule. And here's the kicker. The rule they come up with is only as good as the examples we give them.
So, if learning hinges entirely on the examples, how do we make sure our examples are flawless? Well, that's exactly where our toolkit comes in. We've got 4 incredibly powerful rules that can transform teaching from a game of chance into an engine for clarity.
All right, rule number 1, and this might sound a little counterintuitive at first. Boundaries matter way more than definitions. We tend to think that learning is about memorizing what something is, but real, deep understanding actually comes from knowing what it isn't.
Okay, so take a look at this. This is your classic textbook definition of a triangle, right? A student could memorize this perfectly. They could recite it back to you without missing a single word.
But does that mean they really get it? Probably not. Because the definition alone, it doesn't give them the tools to tell a triangle apart from everything else in the world. It doesn't build that flexible real-world understanding we're after. True understanding lives in being able to apply the concept, not just recite the definition.
So what's the fix? You got to provide clearer boundaries. Instead of only showing examples of triangles, you show them right next to things that are explicitly not triangles. Now the student's brain can do that critical job of comparing and contrasting. The concept of triangle suddenly becomes crystal clear, not because of a definition, but because of the sharp contrast. Okay, that idea of contrast leads us perfectly into rule number 2. And honestly, this one is the absolute heart of faultless communication. If you want a student to learn one specific thing, your examples have to isolate that one thing and keep everything else the same. If you don't, you're practically inviting them to learn the wrong lesson.
Let me show you exactly what I mean with a classic flawed example. Let's say you want to teach bigger, but you show a big red ball on the left and a small blue box on the right. Whoa! What is the student supposed to focus on? The size, the color, the shape, the position? You've just created 4 competing rules, and you've forced the student to guess which one you mean.
Now, look at this. This is a faultless design. It is totally unambiguous. Here, the objects are the same color, the same shape, in the same position. The only thing that changes is the one variable you want to teach, size. There is literally no other conclusion the student can draw. You've engineered the lesson so there's only one right answer.
All right, on to rule number 3. A lot of the big things we want to teach, like writing an essay or solving a complex equation, are, well, complex.
Trying to teach them all in one go is just a recipe for disaster. The solution is to do a task analysis, break them down into all the smaller, prerequisite skills first.
Think about it. You can't teach someone to write an essay if they can't first write a clear sentence, and they can't build a paragraph if they can't write a sentence. Task analysis just means you identify every single little building block, and then you teach them in a logical order. You build the foundation, then you put up the walls, and then finally, you put on the roof.
And that brings us to our final rule. Rule 4, and this one really ties everything else together. It's about a fundamental shift in your mindset. Instead of waiting for students to make mistakes and then jumping in to correct them, we should be proactively designing our instruction so those mistakes are way less likely to happen in the first place.
This is really the difference between being reactive and being proactive. A flawed design creates confusion and then relies on you constantly correcting it. A good design thinks ahead. It anticipates the common mix-ups and builds in those clear contrasts, like our triangle example, to stop confusion before it even starts. It makes the lesson unambiguous from the get-go.
So what's the big takeaway here? Look, this is about more than just a few clever teaching hacks. The source material argues that once you understand this logic of learning, effective design stops being a technique and becomes something much deeper. It becomes an ethical responsibility. And this quote, this might be the most powerful and hopeful idea in this entire discussion. It completely reframes the whole idea of failure. It takes the blame off the student, the one who gets labeled inattentive or slow, and it places the responsibility right where it belongs, on the quality of our instructional design.
And that leaves us with this final, really provocative thought. What if the achievement gaps we see in our schools aren't inevitable? What if student failure isn't some matter of fate or fixed ability, but is actually a design problem, an engineered problem? Because if it's something we engineered through flawed instruction, then it's something we can re-engineer for success. And if that's true, well, that changes everything.